looking at for in terms of the deep space and lunar exploration programs and concepts that are going out there. So this symposium is going to be chaired by Doug Mattson, so I'd like to introduce Doug.
Thank you, Kevin. So in this session, we're going to have 4 talks. We have a talk first by Julie Robinson, and then Brad Bailey is going to do double duty. He's going to do his talk and talk for one of his colleagues who was unfortunately not able to make the meeting. And then we'll close off with a talk by Craig Kundrot. So first talk of the day here is Dr. Julie Robinson. She began her career as a NASA Science Mission Directorate investigator and then moved to management, where she spent the last 15 years influencing NASA engineers to operate human space flight platforms to enable scientific research. She was chief scientist for the ISS program at Johnson Space Center from 2007 to 2018, and then served a 1-year assignment as associate director for the Human Research Program. She's recently named as the first chief scientist in the NASA headquarters Human Exploration and Operations Mission Directorate, assigned specifically to coordinating a multi-platform research strategy that integrates ISS, Gateway, and lunar surface activities in preparation for Mars. So please welcome Dr. Julie Robinson.
Well, thank you so much. Thanks to Doug and Kevin and Gail and Elisa for inviting me to come and speak with you today. I feel like I get to kind of do a report on some wonderful opportunity I've had to work with a number of my colleagues, both in the Human Research Program and in biological and physical sciences, in thinking about this incredible opportunity we have before us, where for the first time, we would have multiple platforms. We would have ISS available, Artemis with both a gateway and lunar surface activities. And we have the opportunity to really make a fresh start and think about how do we plan to use all of these vehicles together for understanding the human and the aspects of life sciences that affect the human, and the aspects of life sciences that affect planets, and the aspects of physical sciences. How do we think about all of that in a comprehensive way so that we use all those platforms to be sure that we have the right preparation to go to Mars as quickly as possible? And so that is a really fun time. There aren't many times in this agency when you get to go back to first principles. The last time that happened at NASA was over 20 years ago, as people thought through what to do on the ISS. What were the things we would do on ISS? What things would we not do on ISS? And so what I'm reporting to you on is really, how do you think about all of these missions and how much they are an analog for Mars and can be used in a way that will help to prepare for Mars, and in where are the limitations, where are things comparable? And a couple of terms I'll use, I'll talk about DRMs, or design reference missions. Those are things that our architect planner types write down. They say, okay, if we were going to plan a mission today, these are the parameters, and I'll show you some of those throughout this talk. But the key is really thinking about everything from the studies we do on the Earth to the studies we do on ISS to the things that we plan for the Lunar Enterprise. Make sure that all of those things are harmonious and are contributing to advancement of knowledge. So when we went back to first principles, and since the biological and physical sciences, and even the physical sciences of vehicle development, the exploration relevant research is so linked to the humans, we went back to some of the original thinking that had been done decades ago about, and has carried through with the Human Research Program, as we look at the 5 hazards of human spaceflight. So those 5 hazards are the things that put the human at risk when we go into these extreme environments. Things like the distance from Earth, including comm delay, autonomous medical care, or the lack of the ability to evacuate. Isolation and confinement, being locked in a small can with 4 of your closest friends or your closest enemies for a very long period of time. Sleep disorders. A hostile closed environment, meaning that you're recycling your fluids, you're recycling your air, you're breathing whatever you bring with you in terms of off-gassing of equipment, and your environment interactions in terms of your food and nutrition or your microbiome. Also radiation effects, both acute in-flight effects, long-term cancer risks, CNS and cardiovascular effects, and then altered gravity fields. things like balance disorders, fluid shifts, etc. Well, when this thinking was done 20 years ago for our use of ISS, the recognition was ISS is primarily about that microgravity environment, that long duration microgravity environment. And in fact, we then turned to ground-based analogs to help us study these areas. So for example, doing radiation work primarily at the National Space Radiation Laboratory, primarily with mouse models. Studying isolation and confinement and distance from Earth, we do in analogs where we try to simulate missions, but they're here on Earth, nice and safe, buttoned up. So things like Hera or the NEK facility in Moscow you see here. For altered gravity, we do bed rest studies in facilities like NVHAB, or we do zero gravity flights. And to study both hostile closed environment and distance from Earth, we also look at Antarctic overwinter studies, looking at the scientists that are there and how they cope with those environments. So those are all analogs, and sometimes people think ground-based is the only kind of analog that there is. But in fact, we can think about any spaceflight platform in terms of its fidelity as an analog across those 5 different hazards. So I'm going to show you a set of charts, and each chart is set up in the same order. I've sorted the missions by duration. So you start with a Gateway Phase 1, 6-day mission, 6-day mission that would be Artemis, sort of 4 days on Gateway, 2 days on the surface, kind of the first Artemis mission. 30 days on Gateway, which would be an extended period of time, possibly 60 days, a 30 plus 30, which is not a real planned mission. It's just something that's made up as an interim kind of a design reference mission. 6 months on ISS, which is what most of our recent missions have been. 12 months on ISS, which we just did the first 1-year mission. You heard Chris Mason talk a lot about the importance of having more of those. 12 months on Gateway. This would not be a crewed time on Gateway probably, but more of leaving equipment or experiments up there to operate for a period of time. And then the Mars design reference missions are shown after that. And so what these bars show you is how much time on these missions a human would spend or a piece of equipment for that matter, would spend in a microgravity environment, in a lunar gravity environment, 16G, or in a Mars gravity environment. And what you can see, the first thing you draw from this is that we don't have anything that looks like those 3 Mars missions on the right. The 22-month mission is one that's looking maybe more likely, hasn't been definitized yet. The 30-month mission is what we call Mars DRM-5. That's about 6 years old. That was assuming that we would have a 6-month transit capability to Mars. That propulsion, advancing in propulsion technology has not emerged. So that mission, although it's the published DRM, is not going to happen. And then if you took solar electric propulsion of today and went to Mars, you'd be in that 12 plus 18 plus 12 kind of mission. So these design reference missions are challenging, and they look nothing like the missions that we're good at carrying out today on the ISS. However, you can also see that the ISS is an incredibly close to being parts of those missions, at least, with the way that we're operating today. So you can also look at radiation. These are all, once again, in the same order. And this, I'm showing the astronaut mission exposures, including vehicle shielding, assuming that the crew members would go to a safe harbor when there's a solar particle event, so that they're protected from those surges of radiation. And here it's just shown in milligray, just the straight up physicist viewpoint of radiation, not trying to tease apart or make assumptions about effects of different kinds of radiation. And what you see here is something that we don't always think about, and I'll show you another chart that shows you the way we generally have been representing this radiation at NASA and why those two are different. So if you focus in the middle in the 2 blue bars, you see the 6-month ISS mission and you see a 12-month ISS mission in milligray. And then next to that, you see what 12 months on Gateway would look like. And you can see that those overlap significantly. Well, you've heard a lot of people, you probably said it yourself, well, Gateway has deep space radiation, ISS is protected. ISS is in the magnetosphere. And so this is kind of surprising when you frame it in this way. And the reason that this is so surprising, or is not the way you're used to looking at it, is because this is often the way that we at NASA have portrayed radiation risk. This includes vehicle shielding and a quality factor for cancer risk based on the work at the National Space Radiation Research Lab. And it's shown in a unit called millisieverts. I kept the graphs proportional, so the units aren't the same on each of these 2 graphs. And there you see those blue bars much smaller and the white bar for 12 months at Gateway much larger. Well, so this is an appropriate state of knowledge for what we know about cancer risk if you think that cancer risk is the most important risk to think about. Well, if we're interested in growing plants for food, cancer risk is not the most important thing to be thinking about. And so what that previous chart shows you is that we may have been missing some opportunities or not thinking about some things we could have done on ISS with radiation, where we've got those durations. What it also shows you is depending on the duration that you're on a lunar platform, you may not get enough radiation to matter for anything. So you've really got to think about not only the kind of radiation and your assumptions about what kind of effects you're looking for, but also the duration in order to be sure your analog is going to tell you something about the mission that you're referencing. So another risk to look at is isolation and confinement. And in this area, you could use a variety of figures of merit, but I pulled one of habitable volume per person. You can see on the left, those early lunar missions are relatively small because they're, and you saw Jim Green present this, some of the early stages of Gateway, those volumes are small, the habitats are small, so they're really not even up to the standard. We like to think of about 25 meters cubed per person for a long duration mission, like a mission to Mars as a minimum. On ISS, you can see it's pretty much a palace. Even if you imagine closing off certain hatches and trying to confine the crew in a smaller volume, it's incredibly difficult to do that, by the way, and do it safely. So we can't find a way to truly do that. But I show you some of the numbers that you get there. And then you can see what the Mars reference missions are looking at, depending on the kinds of assumptions you make about those. So volume is incredibly important for psychology, and different platforms can be better or worse analogs for those kinds of studies. Hostile closed environment. Here, I couldn't find a good figure of merit to look at this in a quantitative way, but I could kind of group things. So I coded things orange if they're Mars-like, and blue if they're ISS-like, and green if they're Earth-like. And you could think about your exploration atmosphere, CO2, the microbiomes of the built environment or of wetted environments and life support systems that might sit there unoccupied for a period of time, and then you come back and want to start them up and start drinking the water again. That has interesting perspectives for the microbiome. The microbes outside, are they colonizing? Are they spreading onto a planet? Is this a planetary protection kind of situation? The food system, whether it's prepackaged, whether it includes crops, or whether it includes bulk foods and cooking and other kinds of assembly or 3D printing of food. And then the dust environment. And so you can see that none of these are perfect matches for each other, and you've really got to be smart about the way that you look at different analogs and different kinds of questions. And finally, distance from Earth. Here, the kinds of parameters you would think about are communications delay, how readily can you talk back and forth to the ground, blackout periods. On a Mars mission, you'll have up to a 2-week blackout as the planets align in different ways. The evacuation time, which goes from 3.5 hours to 2 to 3 days, maybe 7 days, to 9 to 12 months when the window opens up that you can get home at all. And then how you use autonomous systems. How much do you have to have on board versus how much can you rely on from the ground? So in looking at all of these things as analogs, I'm going to now present 2 different sections. First, I'll talk about some things that we've identified that we could do on ISS that would make it better as a model analog for future missions to Mars that would really help us learn more about the human and integrated human systems. And then I'll talk about how this same thinking can be applied to Gateway and the lunar surface activities coming under Artemis. So this is kind of a Goldilocks chart. This is the way ISS is today, the way we've used it for the last 20 years. We've got a really nice match for Mars transit microgravity, and we all know that, and that's what we've been really working on primarily with our human studies. The hostile closed environment is not quite the same. The atmosphere and the environment have been variable over time. We've had high CO2. We have continuous infusion of microbes over time. And the radiation environment, there are definitely differences. In terms of galactic cosmic rays versus protons. From an isolation, confinement, and distance from Earth perspective, it's not a very good model at all. So this is what we've been studying for the last 20 years. Well, we did a joint study between the ISS program and the Human Research Program, and identified that we could use ISS to prepare for Mars in much more innovative ways. We can look at our durations, add isolation and confinement, simulate autonomy and communications delay, simulate the medical response, simulate surface operations after a long transit. There are a variety of things we could do. Now, these things are not easy because these things start affecting your operations overall, and they make it harder for other users who might be trying to do something in that same time period. So you have to be smart about it. But we were challenged to go look at how could you do some of these things, and would that be valuable enough to be worth maybe making temporary changes in ISS operations? And we found if you do all those things, you can improve the Goldilocks chart significantly. You can start replicating deep space duration and conditions if you define your missions differently. You can simulate the volumes in isolation potentially, and you could simulate autonomy and communications. So we identified under that then 4 different use cases that were brought to the ISS program and at least agreed to philosophically. Now, the devil's in the details, and how you get a program to implement some of these things is not easy at all. The first use case is one that you already heard Chris talk about this morning, which is really getting this duration down. So if it's a 1-year transit to Mars and a 1-year transit back, we better understand 1-year missions much more than we realized we needed to do 5 years ago. So that means doing the same research on different platforms over different timescales, making duration your independent variable. So not just studying more 1-year crew, but actually collecting the same data on 6-month crew, on 1-year crew, and on 6-week crew members, so that you can really start understanding something about duration. And we need about 10 more subjects in order to get to a point where we'd be willing to say that we know something about the effect of duration all by itself. And then we need to take another look at that and see, do we need longer durations based on the design reference missions of the day? As we think about this, and we talk about it with our Russian colleagues a lot, it's interesting to look back historically and say, okay, well, if a Mars transit class duration is 9 months or longer, how many people have flown that long in the history of humankind? And you can see that most of the crew members that have flown that long so far in that green bar, they're crew members that went to Mir for 9 to 14 months. And some of those were several decades ago. So think about what your doctor measured in terms of monitoring your health 20 or 30 years ago, and that's what we know about those crew members that flew in that time frame. So then you see in blue the ISS missions. You see Mikhail Kornienko, the Russian cosmonaut that did 1 year on ISS, and you see 3 US crew members, Scott Kelly, but also Peggy Whitson and Christina, who will have had at least 9 months or longer on ISS. And then in gray is this idea, this proposal, that we would add additional information with the full suite of biomedical measures and standard measures that we can take today to really understand this effective duration. And of course, what we'd like to do is not this chart. We'd like to actually collaborate with our Russian colleagues and fly those missions together. And we're talking about that quite a bit right now. Another use case is to take the Boeing CST landings, which are really precious, and start using those as analogs for Mars. We worked with our Mars architecture teams, and they identified a number of mission critical activities that have to be done in the first 24 hours you land on Mars. And if the crew members cannot carry those things out, things like connecting to power if the automated connection doesn't work, you could actually have what we call a bad day, or really lose the mission or lose the crew. So we know that crew members are really having trouble with gravity transitions in that first 24 hours. By 48 hours, they're doing a lot better. But these are driving, when we looked at these with the teams, your assumption about whether the crew member could do it in a week versus in 48 hours versus in 24 hours could make a difference of 50% of the mass of the lander. If something affects 50% of the mass of the lander, it is a complete engineering driver for whether or not that mission can be done. And so that means the crew member and their ability to perform and understanding that variety is absolutely critical. We've worked in Kazakhstan with our Russian colleagues and taken measures under an experiment called Field Test of both astronauts and cosmonauts. And now we're actively working with our Russian colleagues to define a set of missions that we could do together, combining both the Boeing landings and the Kazakhstan landings, and looking at that longer time frame. And instead of just looking at basic sensory motor function, look at more mission relevant function. Can they do tasks like robotic tasks or a contingency EVA if they needed to do it to survive? Doesn't mean they would do an elegant contingency EVA or that every crew member would be able to do it, but can they actually do this for themselves if needed on the surface of Mars? A third use case is to look at autonomy in medical care during 1 to 2 day simulations. So right now today, we do video cons with flight surgeons. Those flight surgeons have relationships with the crew members. They talk to them all the time, and they make decisions about their health from Earth. Well, as we start thinking about a Mars mission paradigm, we have to change the way we do medical care. The crew members have to be the prime medical care for each other, much more like an Antarctic over winter. When they do communicate with medical personnel on the ground, they have to do it store and forward, not necessarily with the ability to talk real time. And ideally, they need all the information and all the support for the equipment they need to use on orbit so that they don't need to wait or be dependent on any communication with home. So we are starting some contingency operations simulations for crew members doing diagnostics on each other without support from the ground. That will be a first time ever accomplishment in space. And then we'll begin to move towards 1 to 2 day simulations on orbit. We already do these kinds of simulations to be sure the crew's ready to respond to something. So here you see a crew member practicing CPR to keep up to date on their medical qualifications. But what we're talking about doing is making these more mission relevant. And this is as much for the crew to learn as for the ground control to learn, both the medical operations as well as the flight controllers. A fourth use case is to look at the overall ability of the crew to be autonomous. And this includes hardware being autonomous, not needing input from the ground, crew being autonomous, being able to plan their own day without consultation with the ground, and being able to solve their own problems, troubleshoot their own hardware, and not rely on backrooms of people that can go solve things for them. And then finally, there is also just plain blackouts. How do you work with a crew? How does the crew work with mission control when they know a blackout's coming? They're going to have 2 weeks without communication. We're used to having, minutes without communication. And so this is a huge change in operational culture. You can test these things on the ground, but when you test them on the ground, it's not real astronauts. It's not real space flight. And we may be missing things. We may not be thinking about these kinds of parameters properly. In addition, if we do it in space, we can start understanding the effects on the psychological health, some of the other aspects of the astronauts that could really enlighten us on certain countermeasures or changes that need to be made in the way that our crews operate. So just to give you kind of a status across those 4 use cases, as I said before, the ISS program manager and the human research program manager have both agreed that these things should be done and that there should be a way to do them, although they're leaving it to the teams to figure out exactly the details of those, and those will be working their way through the implementation boards. A key consideration is making sure that we can do these things in short periods of time when we change the operations, and then get things back to normal for other kinds of users that are doing cell biology experiments or whatever. So for 1-year missions, we have NASA, CSA, and both French and German space agencies involved. The Institute for Biomedical Problems in Russia is still working on, with their management on how they might participate in additional 1-year missions, so we're really supporting that. And then for landing simulations, medical simulations, and autonomy simulations, we and our Russian colleagues have committed to work on those together, and we have a number of international discussions ongoing, international workshops planned, so that our other partners can identify the kind of work they would like to do. If we have a 2-week autonomy window, we want to find all the science that should be done in that window, cluster that together, and then after that window's over, we can go back to normal operations and do the other experiments. International participation in these is critically important. This is not just a nice to have, but it's critical because we know that international crews will be what the crews look like when they go to Mars someday, meaning that all of the nations that are working together in human spaceflight need to have the same lessons learned on crew assignment, on how to manage the psychological support of multinational crews, how multi-language affects your ability to work in communications and in autonomous systems, and to make sure our ground systems all have the same lessons learned and we can really converge on an approach. I think about the difference in the way we operate on ISS today compared to the way we operated in Expedition 1. We at NASA operate almost entirely differently. If you took those flight controllers and put them in a time machine and brought them to ISS today, they would be absolutely shocked at the things that we think are perfectly fine. But similarly, what's interesting is to see how our Russian colleagues started in one place, even with all of their Mir experience, and we started in a very different place, and we've both evolved to a much more common place that is different than where either of us started. We need to extend that to the full suite of spacefaring nations that will collaborate so that we converge on a common set of operations and countermeasures. So there are 4 use cases that we're still tossing around. Some are probably easy or easier, and some of them are incredibly hard. And so we're still discussing those. They're not done yet, but they are challenging. One is we would really like to do some studies of isolation and confinement in exploration volume, so 25 meters cubed per person. Right now, we're primarily doing that in Hera, but it would be really nice to see if true astronauts in spaceflight have the same kinds of biomedical responses to that confinement as we see in our ground analogs. Also looking at food system demonstration, we're planning to do a chamber study with food system demonstration and a variety of human research parameters on Earth, but ideally you would also then do that in space with real crew members so that those restrictions on the food system for exploration may look quite different than what we're used to on ISS. So they've really tested all of that, and you can identify improvements that you might need to make. Logistics validations are something that we probably are going to start soon. Just looking at, if you imagine on January 1st, this is what I thought I needed to operate the ISS for a year. And on December 31st, let's look back. If I had been going to Mars and could not get resupply, was I right or was I wrong? So these are almost paper studies that you can do, but nobody's been doing those. And we're now working to define a set of studies that can use the entire database of everything we've done on ISS to see if we can validate our logistics approaches. And then finally, in autonomy and communication simulation, right now the ISS program is only willing to go to 1 to 2 weeks, and we think it could take 4 years and a really complicated plan to get the operations community to that point. But that point is not close enough to spaceflight, and ideally it would be nice to go 30 to 45 days so that you could validate the simulations that we do in facilities like Hera. So this is a stretch goal and one that we'll keep looking at. We're going to need the information that we gain from trying 1 day of comm delay and then 2 days of comm delay or 2 weeks of blackout. We're going to need those lessons learned before we can even define how we might extend to longer durations that start looking more like some of the analogs that we've used on Earth. So now shifting to lunar use cases, because we have some incredible opportunities in the lunar system that we missed early in ISS. Early in ISS, when it was very small and we didn't have KU band, the crew members were communicating via email. Well, that's store and forward communication. That is communications delay, in fact. And it would be really great if we knew what their psychological parameters were, what their biomarkers looked like, what was their sleep like. But we didn't have the resources from those programs to study that at that point in time. They were too busy building the space station for us to collect the full suite of biomedical data. We're in a much different place today with standard measures. And so we need to think through what are the right things to do on these platforms, even early on the platforms when the resources are quite limited. Well, so the first is a no-brainer. Of course, Artemis, as you land on the surface, the next man and the first woman to the surface of the moon, is the best analog we're ever going to have for partial gravity operations on Mars. And it's one where we can actually evacuate people, we can change our mission, we can get people home, and we can really respond to accidents or challenges in ways that we will not be able to do when the crew's on Mars. So those 5 hazards line up really nicely, with the only 2 differences really being 1/6 or 3/8 gravity, and the durations may be slightly different, and the dust is different, but you do have dust in both of these to grapple with. But there's more than that here. So here's a Goldilocks chart. If you think about the Lunar Enterprise as a Mars integrated mission analog, meaning both your transit to Mars as well as your time on the surface, as well as your transit back. So there you've got a really good match for microgravity, you're close for partial gravity, you've got a good match for a hostile closed environment, especially some of, say, Artemis phase 1, phase 2 is gonna look a lot like probably our Mars missions will look like in those first missions. And depending on your duration, you've got a better match for radiation and a better match for isolation and confinement. But depending on duration is the real kicker there. It could match or it may not match. So as the Human Research Program and Biological and Physical Sciences thinks about this, we kind of identify what are the top things that you would really try to accomplish in monitoring and understanding, doing research on the crew members and the environmental system and the space biology in Artemis. And one is really adding understanding and mitigation and validation of the human health and performance risks that we think crew members will encounter on future Mars missions. But also thinking about multi-environmental integrated research areas. So always you should use the test. If you can do it in low Earth orbit, you should do it in low Earth orbit, and you have no business doing it in the lunar system. And the reason I say that is because you're at least, just by logistics, just by distance, you're an order of magnitude, it's an order of magnitude more difficult to do research in cislunar space, either on Gateway or on the surface. So if you guys are really happy with the access you've had to ISS, and I haven't met anyone who's really happy about that because it's hard to get to ISS and get your research done, multiply that, imagine it 10 times worse, and that's how hard it's going to be to do research in the lunar enterprise. So if you can do it in low Earth orbit, you should do it in low Earth orbit. It's much cheaper, it's much more likely to be effective, and it's even worth thinking about if you could do it partly in low Earth orbit. Can you kick the tires, get all the kinks worked out so that the one shot you get at doing that same experiment in the lunar system, you do the right experiment? I think that's really critical as we think about radiation microgravity interaction. That's obviously something we can look at on the moon, that and radiation partial gravity interaction. But if you don't do the absolute right experiment, we're not going to have the throughput that we have on ISS to really assemble a bunch of information and just keep reflying until we figure it out. These environments, it's going to be a number of decades before we have really ready access, even in going to the moon to stay and to be on the moon sustainably. It's still going to take a long time before those logistics and the challenges of getting there and doing the work even out, and we can get information over the long term. So some of the things that bubble out of that are validation of the crew health and performance system, which on day one will not be the final exploration crew health and performance system, but perhaps 10 to 15 years from now, will start looking more like what we would take with us to Mars. Also, food system and food production, because those things become quite different in different trade spaces, depending on your crew time, the meaningful work of the crew, and whether you're constrained by light, by volume, by mass. All of those things mean a transit food system is probably different than a lunar surface food system. Then how the microbiome of the humans and the plants and the food, the vehicle, the biocorrosion, and how that all interfaces to planetary protection have some huge opportunities to perhaps study that on the moon before we go to Mars. And because once our microbiome does what it does when we get to Mars, it's there. We're not going to be able to get a do-over on that. So using the moon to study some of those processes, the spread of microbes that might vent out of EVA suits, things like that, could be incredibly valuable. And then looking at your autonomous egress, your surface operations, your long-term habitation operations. So these are the kinds of ideas that HRP and SLPSRA was tossing around. But I want to put this in a bigger context, not just from the point of view of one particular research organization, but really even thinking about technology demonstration. So this graph has kind of time across the bottom. So at the bottom right now, we're in this ISS phase. There's an ISS transition phase where there's more and more commercial operations, perhaps a commercial module attached to ISS. And then we'll transition where ISS is worn out, and we then have commercial providers providing access to low Earth orbit. We're always going to keep using ground research to help us as analogs to understand these processes, because we'll never have access to space that it makes it as easy to do as trying to hash out different questions on the ground. But then we'll always need to go to space to validate the things that we think we've learned. And so we'll also always need access to ISS or low Earth orbit after ISS is transitioned away. And then as we move over time, we've started with risk reduction, where we're really focused on single risks at a time, whether that's the risk of vision impacts or the risks of cardiovascular or CNS issues from, we work kind of one risk at a time. But we need to make a shift where we start thinking about integrated hazards, like microgravity and radiation together, and use our analogs smartly on those integrated hazards. And then as we gain that knowledge, we shift to a period where we're looking at more systems testing, where we're really looking at not only the human system and how it's interacting with multiple hazards, but how the vehicle system and the human are combining together. And are those systems ready? Is our understanding of the human ready? And is everything prepared enough that we believe we can have reasonable mission success on a Mars mission? And so eventually you get to the point where you're ready to do Mars mission testing. You think you know the vehicle you're ready to take, and you then have to figure out what things do you need to run in orbit to be sure you've got the reliability and that everything's going to work the way you think before you send them off on that trip to Mars where you can't turn around and come home. So you saw Jim present these charts, because this is kind of the culmination then, as you think about everything I talked about today, how do you use each platform for the thing that it needs to be used for? And so taking crop production as an example, on Earth, you research and develop your crop system. And any of you have seen some of the systems that they're testing at KSC, whole environmental chambers full of different crops that they're evaluating, and that's really important. On ISS, that's where you would do the research and develop the technology for microgravity crop production and get the reliability right, because that's really driven by microgravity. For Gateway, you don't, you know, at some points in time we've talked about, oh, let's have lots of plants on the Gateway. Let's demonstrate an exploration garden on the Gateway. But you really probably should do that in low Earth orbit first, because microgravity and getting the water right is one of the biggest problems you have for plants. Once you get a system that's reliable, then maybe you think about, well, what about deep space radiation and seed viability? Maybe, you know, some packets of seeds sitting in those systems, double checking that those seeds are going to do what you need. You don't want to be coming home and all of a sudden, on your way home from Mars, all of a sudden the lettuce you were going to grow that was going to be your source of vitamin A is not viable anymore. So some of those things are really important. And then validating that Mars transit crop system could be important, but that doesn't require actually feeding the crew for a year. That just requires making sure that the system performs the same way it does in low Earth orbit. Then if you get lunar surface access, starting to think about 1 year, how you crop on the lunar surface, how do you deal with dormancy, how do you do robotic cropping, those things, the possibility of testing some of those on the lunar surface in partial gravity becomes important. And ideally, when that Mars Design Reference mission is ready to go, you've got the transit and the surface food systems that are ready, they're validated, and we trust them enough to provide nutrition for the crew. And you can think about the microbiome in a similar kind of way, looking at what you can do on ISS versus how you examine deep space radiation and intermittent occupancy on the Gateway, how you look at the planetary spread of Earth origin microbes and metabolites on the surface of the moon as people start doing EVAs and working around that area. And then how does that inform the way you structure your planetary protection and your microbiome of your eventual Mars habitats and Mars operations. So similarly, you can think about physical sciences in the same way, and I'm not going to go through this chart in great detail, just to mention that, you know, for physical sciences, there are a lot of things where we don't know any reason you would need to do anything on the Gateway, but once you get to lunar surface, that partial gravity factor becomes really important, whether that's dust mitigation, 16G and cryogenic systems, tank transfers, flammability and fire safety. It may be that, and some of you in this room know that 16G may be the perfect storm from a flammability perspective, much more flammable than microgravity or Earth gravity. And looking at regolith extraction, solidification, materials performance. So those are some of the kinds of things that physical scientists need to think about. The only case that we've come up with where Gateway was really important in these particular lines of research was where there were exposure facilities for deep space radiation and thermal or residual dust. So making sure we can manage materials performance. For human research, I actually have a chart that we're still working on and finalizing that is of that other format, but it's much more detailed because there's a lot that integrates together with the human. So just in the interest of time, instead, I'll show this chart saying, you know, we've got our human research, it feeds to our health and medical standards, which feeds to our crew health and performance system. And you've got these building blocks working on their way up. Each time you build a new crew health and performance system, you want that to be more Mars-like and have more appropriately integrated hazards, and you learn from each of those steps along the way. So just to summarize, in a single chart, we've got ISS as a platform, or low Earth orbit after that. We've got the Gateway, lunar orbit, and we've got lunar surface activities. And each of them has a key use that's distinct, right? So ISS is a microgravity transit analog, deconditioned crew landings, but it's limited by its high levels of activity and large size. We could evolve it, should we desire to do so, using commercial LEO as an analog. That may give us some smaller volumes someday that might become the really appropriate case to compare to Mars transit. Also let us look at confinement and closed environments. For Gateway, for NRHO, we can start monitoring of environments and crew on the Gateway, especially understanding these small volume early mission windows that we missed on ISS and did not learn about is really important. And that's hard to do because this is a time when it's really hard for a program to provide research resources at all. They're trying to build and do their first operations, which are risky. And then using lunar surface as our Mars surface analog, recognizing that there are some differences. And I think as we start looking at lunar integrated missions, using these increasing durations, really thinking about how long are we on Gateway? How long is the crew there before they go to the lunar surface? And then how long are they on the lunar surface? And how does that compare to future missions? Help us learn those lessons and be ready for Mars. Thank you so much.
We probably have time for one, maybe two questions.
Great talk. I'm curious for some of the other things for planning is some of the dust on Mars versus some of the tests on dust that have been for the moon. Is that the Curiosity wheels, for example, had to be replaced for the Mars 2020 rover with different wheels because the dust was so distinct? Do you think that has any implications for some of the health measures?
Yeah, so recently the Human Systems Risk Board really looked at dust as a risk. And you'll hear in the media a lot of talk about Apollo astronauts and the dust being so horrible. But one of the things that happened in Apollo is they didn't use basic personal protective equipment that we would use here. So we know how to deal with silica dust here on Earth. We have miners that do that. They use breathing apparatus. They use filters. We have HEPA filters in all our spacecraft, which they didn't have in the Apollo days. So our Human Systems Risk Board, as they look at that, they don't feel that there's an open question about how do we manage this dust. There are some interesting questions about the static properties of lunar dust, which is not true on Mars. Mars is much more of a geological dust that we're more used to dealing with. But so you definitely have to look at those things. And one of the beauties of the standard measures approach is if you have the standard measures on people in your ground-based analogs and on people on ISS, and you get those same measures on the crew that are working in these early lunar missions, you'll be able to double check that. And if it turns out you're wrong, you'll identify it right away. But right now, what the Human Systems Risk Board is thinking is that primarily we know how to do that with the technologies we have.
Great, thanks.
Great question.
So thank you very much, Julie. Our next talk is by Dr. Brad Bailey. Dr. Bailey's been working at NASA since 1998 with time off to explore the deep ocean biosphere and tie in some astrobiology investigations during his PhD at Scripps. For the past 10 years, he's worked as a senior scientist and then the deputy director for the Solar System Exploration Research Virtual Institute, working to integrate cross-disciplinary research associated with the moon, the asteroids, and Phobos and Deimos. He recently started work at NASA headquarters as the Deputy Associate Administrator for Exploration Program Scientists, where he focuses on the science associated with robotic exploration of the moon. Everyone, please let's welcome Dr. Bailey.
Thanks, sir. Well, thank you to the organizers for allowing me to come talk to you about current and upcoming opportunities for getting payloads down to the surface of the moon. As mentioned, I am actually not the Deputy Associate Administrator. I work for the Deputy Associate Administrator, Steve Clark, and he's the DAA for Exploration at headquarters under S&D, and I am his program scientist. We have a very small group there. Ben Bussey is the chief scientist, and then we also have a few others, a few engineers that are been working with us as well. Let's see, this next slide, great. Top green button, great. Okay, so many of you have seen these and probably most of you know them by heart more than I do, but there have been a series of policy directives that have been put out recently, SPD 1, 2, and 3. The first one really focuses on human space exploration and getting humans back to the surface of the moon. Currently, our target is 2024, and we'll talk about the science that we're expecting to get done, not only ahead of that with precursor missions, but also what the crew will be doing on the surface once we get there. SPD 2 talks about commercial use of space and how do we enable the commercial sector to actually help us get back to the surface of the moon in an efficient, sustainable manner. And then the last one is, of course, on space traffic management. And you can read more about that online if you are more interested. But how we're going to go about this is overall Artemis. I'm sure, again, most of you know a lot about Artemis, but here we have our NASA swoosh charts. It's pretty obvious why it's called the swoosh. But on the top part, which is largely the human domain, we have Artemis 1, which is the first human spacecraft to the moon, which we plan on sending out and around the moon and then back. Artemis 2, which will have humans on board. And then we start to develop the Gateway program, or the Gateway platform. And that first power and propulsion element will be launched theoretically coming up in 2022. And then we have Halo, which is a logistics module that will expand on Gateway, and then we'll have another logistics module. And then finally leading up to Artemis 3, which is expected in 2024, which actually puts humans on the surface. If you stick around for the talk after this, I'll talk a little bit more about Gateway and what that actually means. But on the bottom part, you can see that we're looking at doing several precursor missions to get payloads to the surface and start to understand more about the surface science on the moon, but also what data sets are required for us getting humans back to the surface in order to buy down risk or enable long-term sustainable habitation on the surface of the moon. And so with that, we're doing the commercial lunar payload services on the bottom left there. And that's probably what most of the rest of my talk is going to be about. But we also have other activities ongoing as well, where we have an early South Pole mission, which is going to be a robotic rover tooling around, looking at volatiles on the surface. And in general, we have a pretty diverse portfolio of lunar research and opportunities for getting payloads down to the surface. This is NASA's attempt to save some money. And so we have a second swoosh chart talking about phase 2. And so here we have Artemis 4 and 5, where we're actually starting to look at reusable architecture for getting humans down to the surface. And then 6, 7, where we actually have permanent human presence on the surface of the moon from 2028 moving forward. Again, we do plan on utilizing CLIPS during this period in order to, and we can use CLIPS to pre-deploy supplies. We can have CLIPS deliver rovers that can go around doing precursor science that the astronauts can then leverage once they're actually out on EVAs. And then, of course, there are heavy cargo landers that we expect to get down to the surface as well for supplies for the human architecture. So this is the LDEP program in total. I'm not going to talk about all of this, but I'll try and focus just on the stuff that pertains to this community. But the things that I want to make you all aware of, that we are really going through and kind of soup to nuts. What does it take to get payloads down to the surface? How do we develop instruments? How do we invest in long-term mobility strategies? And then ultimately we are in development, and it should be released soon, of an overall lunar strategy for what the Science Mission Directorate is planning to do and how we are actually working together across Mission Directorate borders with HEOMD as well as STMD in order to make the most out of our opportunities on the surface. So with that, I talked about CLIPS, the Commercial Lunar Payload Services. And right now what we're expecting is 2 deliveries to the surface per year. That sounds like a lot. And to those of us working on the ground, it feels like a lot too. But it is extremely exciting that we are providing this many opportunities to get down to the surface to do a variety of different research investigations all across the surface of the moon, from polar regions through mid-latitude regions and everywhere in between. Another thing that LDEP is focused on is instrument development and discovery. We're also in charge of DALI, which is the maturation of instruments, instrument concepts. We also have Viper, which is the polar rover I was mentioning, the volatiles investigating polar exploration rover, if I remember correctly. But that's expected to land in late calendar year 22. We're working towards that. It's in joint, it's being built jointly between JSC and Ames. but it's also being delivered by a CLPS provider. So again, we're using these CLPS, this CLPS architecture to deliver our payloads and packages and instruments and investigations in total down to the surface. We do have plans for follow-on rovers approximately every 2 years that will largely be commercially provided. As I mentioned, Viper is largely NASA between Ames and Johnson, but future rovers will likely be commercially provided. We're also looking at how do we invest in long duration rovers, rover technologies. How do we survive the lunar night? How do we can we use AI to do navigation and autonomous roving? We also have taken over operations for the Lunar Reconnaissance Orbiter, as well as several lunar small sats, such as Simplex. Lunar Trailblazer was one of the recent awardees for Phase A-B study. It's being led by Bethany Ellman out of JPL. And we've also approached some of our commercial providers to look at whether they could provide rides for CubeSats and small sats, and then just drop them off in the vicinity of lunar orbit, so that they don't have to figure out how to get all the way to the moon. And then the last thing that I wanted to talk about was ANGSA, which is the Apollo Next Generation Sample Analysis effort. And I'm sure most of you have heard about they're cracking open some of these samples that were taken during Apollo, but then held under vacuum or cryo conditions or noble gas conditions, so that when we ultimately did have enough good analyzing capabilities, that we could unpack them and learn more things that we don't know yet. So that's ongoing right now as well. CLPS. Okay. There were 9 companies that were originally part of the on-ramping process for CLPS. So these 9 companies are available or capable to, or let's see, we invite these 9 companies to provide proposals to us to deliver specific payloads down to the surface. And so these services have been tasked through task orders. And ultimately, we had our first task order awarded earlier this year. And again, we do have an expected cadence of 2 deliveries per year. So there are a lot of task orders, a lot of requests for proposals going out to the commercial community to provide these services to us. You can almost view it as a UPS or FedEx to the moon, where we provide the package, we package it all up and we hand it to them, and they say, great, we'll deliver it to the moon for you, and here's your data at the end. We also have recently undergone an on-ramp for new companies to be a part of this catalog of companies. And basically, we were looking for enhanced capabilities of getting larger mass down to the surface. Viper is on the 300 to 350 kilogram order size. And so we needed to make sure that we had enough companies out there that were able to provide that amount of mass down to the surface. And so those awards, I think, just went out either yesterday or maybe today, but you should hear more about that. And then we also plan on releasing the task order for Viper shortly after, just within the next week or so. So the first 2 CLPS selections that we had were Astrobotic and Intuitive Machines. Astrobotic was awarded approximately $80 million to deliver as many as 14 payloads to Lacus Mortis, which is kind of 45 degrees north on the near side of the moon. Intuitive Machines was awarded $77 million to deliver. We're actually probably going to be slightly more than 5 payloads, but ultimately they are planning on not going to Oceanus Procellarum. This appears to be an old slide, but they're actually going to be going to the southwest corner of Mare Serenitatis, just on the other side of the Apennines from 15. So we are excited that they are going to be taking these payloads, and we right now have expected launch and landing dates of Q3 2021. So I think launch is somewhere around July, landings in September, and for both of them in that general time frame. Now I said there were a lot of instruments that we were planning on flying. These 2, Astrobotic and Intuitive Machines, are flying the payloads that were selected as part of a call called NASA Provided Lunar Payloads, or NPLP. That was an internal call to NASA centers to give us proposals for instruments that could be completed and delivered in a reasonably short turnaround time. So these have reasonably high TRL. They are fairly far along in their development overall. We also are accepting a little bit higher risk associated with some of these instruments because, you know, landing on the moon is hard, as we've witnessed with Vikram, and so we recognize that there will probably be a little bit of an attrition rate. So we are taking a little bit more of a risk with the instruments, but of course we are following all appropriate protocols to make sure everybody's successful. But these calls actually are a mixture of science, technology, and exploration. So, SMD, HEOMD, as well as STMD, STMD, Science Technology Mission Directorate, HEO, Human Exploration Operations Mission Directorate. Everybody has instruments that they are interested in getting data back from. We also had a second call that was opened externally to the broader community, and that was called LSITP, the Lunar Surface Instruments and Technology Payloads, and that was, we selected 12 instruments on July 1st for that. Again, these were also a mixture of science and exploration and technology demonstrators. And ultimately, we do have plans for future calls, both internal and external combined. Where our goal is to, let's see, I'm just going to skip ahead real quick. Where our ultimate goal is to get to PI-led investigations, where we're actually soliciting suites of instruments that work together in order to go after a specific scientific question at a very specific location on the surface of the moon. Just as a completely random example, we would come out and say, our next destination, we expect to go to a lunar swirl, for example, and please give us suites of instruments that you would like to see perform science at a lunar swirl destination. We'll also have the call open to destination agnostic instruments as well, but ultimately we are working with, again, HEO and STMD in order to make sure that that all the various science organizations around NASA have opportunities to fly what they need to the surface of the moon. So as you can see, here is the cadence that we have set up for the first several CLIPS deliveries. And I talked about Q3 21 for the first two, task order 2s, Intuitive Machines and Astrobotic. The 19C and 19D along the bottom, those are going to be the two LSITP payloads, and we currently have manifests set up for those. But then we start getting into the last three, 20B, 21A, and 21B. Those numbers don't mean anything to you. They barely mean anything to me. But we do need to start soliciting a fair number of instruments from the community in order to make sure that these landing opportunities are full. We don't want to leave space on these landers when there are a bunch of really great new science science investigations that can be completed. So we are going to have to start really working with the community in order to bring all those new ideas and the suites of instruments to bear on all these landers. So again, twice a year, there's going to be anywhere from 5-6 payloads going per lander. So there's going to be a lot of really good opportunities for this community in particular, as well as the general planetary science and human exploration communities to be involved. So backing up just a couple slides. Let's see. Here's a nice little chart of how we've split up Astrobotics versus Intuitive Machines. Most of those don't matter that much to you, but you can take a look at the color coding, where green is science, yellow is technology, and blue is exploration. And so we do have a strong partnership with all the various organizations. Here are the LSITP payloads. Again, these are 12, mixture of technology. I think there's the radiation hardening of a computer experiment on there, a variety of different electromagnetics and magnetometers, and let's see, you can read it for yourselves. You also find it online. But there are a lot of good opportunities, again, for the entire community. And these are the next ones that are going to go on the two that are going to likely be flown in 2022. I think that's all I wanted to say about that. Okay, so in general, as I mentioned, a lot of these initial landers are probably going to be static landers. They're just going to get to the surface. They're going to, showcase that these specific companies can get to the surface and provide good, valuable data back to us. But ultimately, we need and desire to have the ability to rove around on the surface in order to get measurements at more than one place. And so we are investing in a lot of different ways to provide mobility to these instruments. And so whether it's NASA provided or whether we push the mobility down onto commercial entities remains to be seen. But ultimately, we want to be able to ground truth volatiles at the poles. How do we know that the orbital measurements we're taking are actually what we see on the ground and that can be ultimately be used for a sustainable human architecture on the surface? How do we survive lunar night? It's non-trivial. And so we do have a variety of different rover development paths ongoing. As I mentioned, Viper, we have a study task order out to existing CLIPS providers to see what they can provide to us. There's also a larger RFI to industry to look at commercial sources and availability. How do we potentially use swarms, for example, to get at the data that we're after? And then we're also engaging the international communities to make sure that they have a stake in the overall operation. A quick note about Viper. Viper is a largest rover, as I mentioned, about 350 kilograms, that will go down to the south pole of the moon. And ultimately, it will last for several Earth months, traverse hopefully tens of kilometers, and all the while using its 4 instruments to produce mineral models of various volatiles on the surface. So we have a neutron spectrometer, a near-infrared spectrometer, a mass spectrometer, as well as the Trident drill being produced by Honeybee. And so between all of those, we expect to be able to do a little bit of a grid pattern in order to figure out where the volatiles exist, in what concentrations, in what forms, and hopefully that can help start to inform some of the STMD requirements for doing ISRU on the surface of the moon, in situ resource utilization. And so how do we then harvest that material? How do we work with it and ultimately make it a usable form for sustained human presence? I talked about Simplex 2. Again, this is a small ESPA class, ESPA plus, I think, size class of satellite, probably about the size of your average dorm refrigerator. And it will have 2 primary instruments on it. The first is an enhanced version of the Moon Mineralogy Mapper, M-Cubed, that flew on board Chandrayaan a while ago. And then we also have the Lunar Thermal Mapper, which will also help determine what the overall composition of the surface is. But between the 2 of them, we'll be looking at between 0.6 and 100 microns on the surface, and hopefully start to tease out some little bit higher definition of where the water actually does reside on the surface of it. I already talked about ANGSA, but I talked about ANGSA, but we are particularly excited. We cracked the first one a couple of days ago, and so hopefully we'll return a lot of fabulous new results from that effort. But there are 9 teams that were selected to analyze various aspects of these untouched Apollo samples. And so stay tuned for more information about that. I talked a little bit about the science strategy on the moon and what SMD is attempting to accomplish with these CLIPS providers and getting back down to the surface, and how that ultimately can help inform humans on the surface. And so really, we are using CLIPS to do precursor robotic missions that will ultimately study volatiles, looking at science both at the poles of the moon, but also non-polar regions, looking at INA, for example, an irregular mare patch, or going to a lunar swirl, or pyroclastics or volcanics. All of these are high priority science investigations that have been identified by the science community through various community-driven documents, such as the decadal, or some of the league sats, or some of the academy studies, such as the SCAM, the Scientific Context for Exploration of the Moon study that was done. So really, we are using those documents to help prioritize where we go on the surface of the moon, and from a science perspective, but then again, how do we actually help understand what needs to be done from a human exploration perspective as well. We do plan on putting out calls for instruments on at least a yearly cadence, if not more often than that. We are sensitive to the fact that there can be proposal fatigue within the community. We're working on various ideas to alleviate that. So stay tuned. We're actually planning on having a town hall, virtual town hall in early December, and I'll work with Kevin and Craig in order to make sure that this community is well involved and able to participate in that as well. But then we're also, again, using our international partners to develop strategies and payloads to get down to the surface. We're in talks with ESA, for example, on working with them on their Lunar Pathfinder program, which is going to be a comm relay satellite that will help us and the CLIPS providers get payloads down to the far side of the moon, because clearly it's hard to communicate with the far side of the moon if nothing's up there. But there will be Gateway, which again, stay tuned for the next talk. But we, again, we are really planning on doing a lot of interesting science from the surface of the moon by 2024. And it's being done through polar landers and rovers, polar surface, again, first direct measurement of polar volatiles, and surface exploration of permanently shadowed regions on the poles of the moon. We're also, again, going to non-polar regions with landers and rovers. And then we also plan on doing with orbital data, similar to what I was just talking about with the simplex. And then also we have in situ resource utilization, initial research, and hopefully trying to answer some of those questions that that ISRU researchers have on availability and how do they actually pull those materials from the ground and use them. We're also working with HUMD to develop an implementation strategy with the crew once they're there. What types of science investigations will the crew actually do once they're on the ground? And so we're looking to the community to help develop ideas for science to conduct on the lunar surface. And we are working closely with HUMD as they move forward and actually do the selection of the HLS architecture. To make sure that science is being well represented in that effort. But through some of the stuff that we do with CLIPS, we can actually do surface reconnaissance. We're also looking at concepts of operations, or ConOps. How does a science backroom actually work with astronauts sitting on the surface? And we are also working with the curation facilities down at Johnson Space Center to ensure that they are prepared to receive these samples, of course, when we bring them back. But also, how do we collect the samples in a clean manner, such that we can actually get at the science that we actually want to from them. This is the last slide, perhaps, but we do have a joint SMD, HEO, and STMD workshop planned for April in order to discuss the science being enabled by crews getting to the South Polar region. And again, we are looking at, because this is a HLS, human landing systems, requirement within 6 degrees of the pole, what are the highest priorities from a science perspective that the crew should prioritize visiting, and what science can actually be achieved? That can include surface science experiments that might need crew interaction to in place, or crew to actually do the experiments, or just deployed by the crew. And also what technology is actually required for us to develop prior to that happening as well. So you should see a community announcement come out about that. You must submit an abstract in order to participate in this in this workshop, but we're expecting it expecting it to be a similar sort of thing to what the science from the Gateway workshop was at the beginning of last year, 2018. If you're familiar with that. If not, then you can Google for it, and they have a really nice report up on the website. And I think that's it for me for this presentation. Should we stop and ask questions now? Okay, all right, sure. So Jake Bleacher is the Chief Exploration Scientist for HEOMD. He couldn't make it, so he asked Debra Needham, who is his deputy, to come, and Debra couldn't make it. And so approximately an hour before this session, they asked me if I could give these slides. So I haven't really seen them much, so wish us all luck. I suspect some of it's going to be overlap with what I've heard, so if you listen to my first talk, then feel free to doze off for the next 5 minutes. So again, Space Policy Directive 1, et cetera, United States lead the return of humans to the moon, followed by human missions to Mars and other destinations. And so getting forward to the moon, this is what we're charged with, and this is what we're trying to accomplish. Getting to the moon by 2024, going with commercial and international partners, proving ground to test technologies for Mars, as Julie outlined so eloquently earlier. We also are looking at sustainable and reusable architecture, ultimately hopefully keeping costs down overall. And then ultimately Gateway is a key component in this mandate as NASA is planning moving forward. Again, swoosh chart number 1, swoosh chart number 2. But again, we really are focused on reusable lunar human lander elements and how does Gateway actually fit into this overall architecture. And basically, Gateway is an opportunity for us to enable reusability and sustainability. And in its current orbital plans, it can provide access to the entire lunar surface. It can support lunar vehicle checkout, such as if HLS sends up its ascent and descent elements, and then it can attach to the Gateway and waiting for Orion to deliver the crew, then it can actually undergo lunar vehicle checkout while it's waiting there. So it's almost a congregating point for the architecture to get humans down to the surface. It allows for deep space systems testing. It's a platform, again, as Julie was mentioning, that provides us an analog to deep space exploration and something that low Earth orbits can't always do in all situations. It is an international and commercial partnerships. There are several international partners at the table that will be providing various components to the Gateway and ultimately can be a stepping stone to Mars exploration. Again, parroting what Julie said earlier. So currently the Gateway orbit, lots of different types of orbits out there. What we've settled on for the moment is a near rectilinear halo orbit, NRHO, where it's got an apogee of 70,000 kilometers and a perigee of 1,500 kilometers at its closest point to the lunar surface. But this orbit actually gives us a lot of positives. It gives us a communications platform. Again, as I was talking about, we need far side communications in order to do anything from the surface, including sample return from South Pole Lake Basin or telerobotics from the surface. So it can provide that. It also gives us let's see, a staging point for planetary sample return missions. You can actually have a Mars sample return come back and park at Gateway until we're prepared to receive it. There is the deep space environment, as was already mentioned, that can help us understand what the overall environment on deep space exploration looks like and what the hazards and risks are to our astronauts and the equipment therein. And so right now the NRHO is the flavor of the month for the orbit on where it's going to be. So currently Gateway has 2 phases, and this lines up with the Artemis phases. Phase 1 is the initial deep space vehicle that includes the power propulsion element, PPE, as well as the halo and the the logistics module. In phase 2, we actually are planning on continued construction of the gateway, enhancing the gateway with more living space, ECLIS, environmental control and life support systems, and overall science capabilities. CSA has formally agreed to provide external robotics similar to the arms that they're quite good at. And we are currently in negotiation with other ISS partners to provide other components to the gateway. This is why we think Gateway is an integral cog in the humans to the surface. Ultimately, it can provide a command center and aggregation point, as I was mentioning, where all the different components of the human landing system can come together, get checked out, and then humans come, and then the two. So Orion will bring 4 people. 2 will stay on board Gateway. 2 will descend to the surface. And we are hoping to establish a strategic presence around the moon with the US in a leadership role overall. But really what we're trying to create is robustness and resilience within the lunar vicinity that we can reuse and hopefully ultimately make getting down to the surface a little bit easier. It is open architecture and interoperable, so the Gateway can receive, for example, one of our commercial partners could decide to send something there and await deployment. So we're looking to make it a flexible platform that can be used by a variety of different agencies and commercial partners. Let's see, so Gateway Phase 1 will provide power, propulsion, and communications for surface landing systems. And it's in the current orbit, NRHO. It actually is accessible for many of the commercial rockets that exist out there. It really can be a safe haven for the crew while the other crew are actually hanging out on the surface. Let's see. Yeah, that's all for that slide. Okay, phase 1 status. The PPE actually is based on commercial satellite bus. It was actually, I think, originally part of the ARM, the Asteroid Redirect mission, and then has been repurposed over to the PPE for Gateway. But it's scheduled to launch in 2022, being built by Maxar. The Halo, which is the habitational logistics outpost, which will leverage Orion life support, but also enhance the living quarters and science capabilities of the Gateway, is being built by Northrop Grumman, is scheduled to launch in late 23. And then the logistics elements we're expecting to launch in 24, just ahead of the Orion crewed flight for Artemis 3. And so maybe this is really the take-home slide. So if you've been sleeping this entire time, now's a good time to wake up. This is what we believe are the real science opportunities that exist for Gateway. And so Julie talked a lot about human health and performance associated with living and working in deep space. So I won't belabor that any further. However, each different element, so PPE, Halo, logistics element, each element actually has plans for both internal and external payloads going onto the surface. So the PPE has a couple of external payloads that we're currently working with our international partners to figure out who's going to develop these payloads, who's going to fly them. There is the Gateway Payload Utilization or Coordination Panel. Anyway, they're actually working with each of the various international partners, JAXA, Canada, ESA. I know I'm forgetting one or two. Sorry? Oh, okay. Feel free to add in anytime you want. Okay. Anyway, so they're currently working with them, developing different splinter groups, focusing on the measurements and then the instruments that need to be taken from those various splinter groups. So one of the splinter groups is, of course, radiation and space weathering. Another one is understanding the local environment. There's an astrobiology, exobiology component to it. Kevin, what's the one you run? The gut biome. Yeah, the biome one. I think there's a 5th one I'm forgetting at the moment. But anyway, so they're coming together and defining what those measurements need to be, and then what instruments need to be developed in order to take them. And we've engaged the broad community, again, as you heard, between Earth, Astro, Planetary, SLPSRA, Space Life Science, Space Life Science Research, you get it, SLPSRA. I know I should know that one. Ultimately, we are looking at how do we use the gateway for lunar surface opportunities, crewed and robotic surface missions. How do we use it for sample return? You could also envision a CLPS lander going down, collecting a sample that we want, and then lofting it back up into orbit, and then captured by gateway, and then taken home by Orion the next time. And then also, Gateway can provide other cislunar locations. There are variations of the NRHO. There is low lunar orbit. There's DRO, distant retrograde orbit, and Earth-Moon Lagrange points that it can all be deployed at. And then, as I've mentioned many times, we can use Gateway for communications for enhanced science capability on the surface of the moon. And so we're looking to use Gateway in a variety of different ways from science across the board. So I think with that, sorry if that was painful, but I guarantee it's more painful for me. Thank you. Oh, yeah. I think there's time for a few questions. And if you have questions about Gateway, I recommend you talk to Jake or Debra. I'm happy to give you their personal emails and phone numbers and addresses, credit card information.
Thanks so much for carrying the water there. I'll actually go back and the question for CLPS.
Yeah.
So you talked a lot about the portfolio of science that comes through SMD traditionally, but not so much about the portfolio of science that comes more from this community and how that would find its way onto CLPS. Obviously, the Dolly and Rose's calls don't really speak to life and physical sciences. Could you say a little bit of something about how this community might get involved in it?
Sure. So as I mentioned, we've got a pretty strong cadence for upcoming missions, and we need to develop enough instruments in order to do that. And SMD doesn't want to supply all the instruments. We do want HEO and HEO SLPSRA, as well as AES, which is the Advanced Exploration Systems part of HEO, as well as STMD payloads. So our future call is going to be called PRISM. It's the payloads and research investigations on the surface of the moon, which I think is infinitely better than the LSIP acronym you saw earlier. But ultimately, what we're trying to do with that call is it's going to be a continuously running call where we will have a modified step 1, step 2 proposal process where you submit a mandatory step 1, and then once we decide which opportunity we're going to solicit for, we will go off and make a call for a specific location on the surface of the moon and invite those from the step 1s that are relevant to that destination to participate and submit a step 2 proposal. The expectation there is that we will ultimately produce a catalog of instruments that are available to us such that when new opportunities arise, we know what the community has to offer, and we know what the limitations or the specifications for each of those instruments actually entail, so that we can make informed decisions on how to provide an extra 10 kilograms say an extra 10 kilograms of mass comes available on a new lander. How do we actually determine what instrument will go there, or an international partner has a specific amount of mass available. How do we figure out which payload we want to send or solicit for in order to send on that? And so the idea is that we will create this catalog of instruments that will be available. It won't just be like Planetary, SMD style instruments, but it will be SMD instruments, there will be STMD instruments, and there will be HEO SLPSRA instruments involved as well. And so from this combined list of our catalog of instruments, we expect to be able to provide those opportunities to this community as well. And just a small note, that's modified mandatory step 1, whatever you want to call it, will be open so that you can actually submit at any time. You can submit that step 1 at any time and just add to the catalog. You may not, but you have to do that in order to get a step 2 invitation. So hopefully this community submits a lot of step 1s, and if there's a lot of strong interest, that gives us a lot more fodder to go forward and solicit for more funding for this community to fly to the moon as well.
Thanks. I think they selected me because I'm usually very hard-nosed about time, but I'm going to violate my own laws because Sandra's standing there, and I think we'd like to hear from her.
Well, just a quick question. On the previous slide, you mentioned science opportunities for Gateway. I could not tell looking at the slide is trying to distinguish between phase 1 and phase 2 for Gateway. Whether a decision has yet been made as to whether there will be any science support capabilities for phase 1 Gateway.
For phase 1, yes. So as I think I was talking about, there are external and internal payloads being solicited for both, for all various elements. So on the PPE, I believe there are 2 external slots for payloads. And so we're looking at trying to figure out, again, what are the measurements that need to be taken, what instruments can take those measurements, and what TRL development, because ultimately this is quick turnaround, as you saw from the schedule. So for something, it has to be reasonably far along in development and high TRL in order to fly on board the initial portion. But as we start developing and creating new elements to the Gateway, hopefully that will relax and allow for a more traditional development period for solicitations.
Okay, great. Thank you.
Thank you.
Well, again, I want to thank our speaker for doing double duty and for doing such a great job on both. Final speaker of this session is Dr. Craig Kundrot. He's the director of the SLPSRA division, the Space, Life, and Physical Sciences Research and Applications division in NASA's Humans Exploration and Operations Mission Directorate. He's previously in NASA's Human Research Program and Microgravity Program. Before entering science management, Craig was an X-ray crystallographer studying structure and function of proteins and RNA. Please welcome Craig.
Thank you, Doug, for this opportunity to share with you folks SLPSRA's space biology and physical sciences and how it relates to lunar exploration as we understand it today. Wow, have things changed since Bethesda 1 year ago? A lot of things were already in work, but in March, when the Vice President gave NASA the mandate to land the first woman and the next man on the moon in 2024, a lot of things went into overdrive and new things came along. So you've heard a lot about this already today. This slide is kind of a Reader's Digest version of some of the highlights. So the overall Artemis program, as you heard, has 2 phases. One is this sprint to get the first woman and next man on the moon by 2024, and thereafter to develop a sustainable exploration program and have that in place by 2028. Major components of this, Brad just gave us an excellent overview of the CLPS program, which is well underway and expecting to, as you just heard, send payloads, twice a year to the moon for the foreseeable future. The Gateway elements have, the power and propulsion element has been procured. The Halo element is either procured or still in negotiation, I'm not quite sure. And proposals are under review for the cargo delivery or logistics module. Also, the human landing system, proposals have been received and are under review for that. So this charge that we received in March has really kicked a lot of these plans into overdrive. So what's the impact in the SLPSRA world? Well, this new era of lunar exploration fits in perfectly well with SLPSRA's strategic framework. So whereas all these lunar plans have been accelerated and changed some emphases, our strategic framework remains in place. And the key part is our twofold mission, to enable exploration on the one hand and to pioneer scientific discovery on the other. And these are not mutually exclusive missions. More often than not, the work done in SLPSRA supports both. So to take 2 examples, the work we need for growing food crops for exploration is going to require a lot of fundamental biological understanding of plants and designing the systems to support them, and possibly genetically engineering and designing the plants themselves. So there's a big interplay between the applications and fundamental understanding of the system. On the other hand, another example, something that started out as pioneering scientific discovery, is the Cold Atom Lab, which started out as a pretty basic fundamental physics line of inquiry, But as we speak today, there are already applications in mind for a lot of the cold atom physics that would provide precision navigation or geodesy as part of exploration. So more often than not, these two missions actually intertwine. So how does the lunar exploration program fit into the framework? Well, I like to think of it this way. For decades, space biology and physical sciences have used a broad range of research platforms to accomplish the work. And now we're adding to the menu or the palette lunar environment ones. So you see on the upper right, the Lunar Gateway. Then we have robotic landers that Brad just told us about, and eventually sustained human presence on the moon. So that top row is a good example of progression of options available to us. We have used CubeSats. We, of course, our workhorse today is the International Space Station for flight. We still use free flyers. We've, in coordination with the Russians, have done over a dozen free flyer missions and are in the midst of planning for the next one. Also in SLPSRA, we just closed out a request for information for free flyers from US industry because we want to sample all the possibilities that might be available in this new era where we're commercializing LEO. And of course, we'll continue to use all the ground-based ones. We will never want to do, propose to do something on Gateway that we could do in a drop tower at Glenn Research Center. So what are these things that we could do uniquely in and around the moon? So first, looking at lunar orbit, as has been mentioned earlier today, there are only a couple things that make it different from the ISS. One is the access to the deep space radiation field. ISS is almost half shielded by Mother Earth, occupying about half the solid angle around the ISS, and it's got the magnetic field around it. Gateway, however, will be exposed to the full galactic cosmic ray spectrum and at the same flux as you would have in transit, say, to the moon or to Mars. So we're very interested in the radiation effects on microbes in the vehicle and associated with the crew and the plants themselves and the crew themselves. It's also another closed habitat. Brad, the term you were looking for, I think, a moment ago is the microbiome of the built environment, MOBI. So if you physical scientists didn't know that yet, now you've got a new acronym to throw out at your cocktail parties. It'll be another closed habitat, like ISS, but significantly different. So like ISS, we'll be concerned about what the CO2 levels are, the humidity, the temperature, etc. But compared to ISS, which has crew or cargo coming, roughly speaking, every month, the Gateway is not going to have that, at least initially, that frequency of activity. And in fact, the initial plans are for Gateway to be occupied for only 1 month out of the year. So it'll be in a dormant state for most of the year. And an active area of discussion is how will the Gateway be maintained during that dormant time? To limit microbial growth during that time, it might be at a lower atmospheric pressure with little oxygen or no oxygen, lower temperature, etc. And then come back up in preparation for crew arrival. So it'll be a whole new system to study from a microbial perspective, which is very important as we look forward to Mars, because in the Mars mission, we'll be essentially in a closed system of systems. We'll have the transit habitat, we'll have rovers, surface habitat, suits, etc. But all that together makes one closed system, which will be evolving for, as Julie's chart showed, for on the order of 30 months or so. So that's the closed habitat is a very important area where we're interested again in the microbiome of the humans, plants, vehicles, and things like biofilm production and biocorrosion. One other element to the Gateway is its distance from Earth, and this is where some fundamental physics experiments like deep space quantum links and the like can be take advantage of the large distance between Earth and a stable platform. But things get particularly interesting from a SLPSRA perspective when we look at the lunar surface. So a lot of this was already mentioned earlier today, but at reduced gravity at 1.6 G, In the combustion realm, there's a lot of concern about flammability and fire safety. I think Julie mentioned that 1,6G might be a sweet spot for flammability of some materials. That's very important to know from a safety perspective. There are a lot of systems that require two-phase flow. So in our fluid physics program, there's going to be a lot of very applied work to help advance the engineering systems that we need for sustained lunar exploration and eventually for Mars. On the materials side, there's soldering, brazing, welding, additive manufacturing, a lot of things linked to in situ resource utilization and sustainable exploration. And on the biology side, just to pick one example of the reduced gravity, is food crop production. We are finding that keeping plants properly watered in that Goldilocks zone on the ISS is quite a challenge. And it remains to be seen how things will be in 1,6G. Will plants and the watering systems behave pretty much like a terrestrial 1G system, or more like a microgravity, or be some kind of hybrid? Radiation is also of interest on the lunar surface. You might think initially it's essentially the same as Gateway, except upon reflection, okay, you got the moon there, so you got half the solid angle, occluding galactic cosmic rays. But Jim Green mentioned this this morning. There's what's called albedo radiation. So the galactic cosmic rays that hit the lunar regolith, some of them hit nuclei and fragment them, some of which send backscatter back towards the surface. So it turns out about 10 to 20% of the absorbed dose to, say, the crew on the lunar surface will come from this albedo radiation. And it's at different particle type and energy levels than the GCR. So that could have different biological outcomes for the crew on the surface. Then we come to lunar dust and regolith. So this is particularly important for sustainable exploration. How do we work with these granular materials in a 1,6G environment? How can we do construction and perhaps create cement like Alexandra's talk told us about this morning? All things that we need for prolonged sustainable presence on the moon. Extracting resources like metals and oxygen from the regolith. And Julie did bring up a good point about how the Apollo astronauts weren't using personal protective equipment. But on the other hand, that dust is particularly pesky. It being formed from fragments from impacts, it is, and not weathered on the moon. It's particularly physically jagged and prone to sticking to things. And this is actually a question back to you, Jim. You can maybe in the question and answer period. I did not realize until talking to Jim Green recently about all this water activity on the moon. And heretofore, I've thought that there was nothing for the regolith to chemically interact with. Whereas, anything on the Earth here has plenty of oxygen and water to interact with. I always thought of the moon as being, having a very little atmosphere, but not much chance to chemically react. So that's a question for you in Q&A, Jim. In any case, dust is, can follow mechanical systems, and that will be a very big area of research. The solar spectrum. Going back to Jim's talk, he showed some very impressive concepts for the use of sunlight to help obtain the water from the regolith. It's also a low power source for growing plants. If we choose not to filter that sunlight, it won't be attenuated by any atmosphere like our Earth, so plants will be exposed to more radiation in the UV and the IR. That could be a good thing or a bad thing, something to take advantage of or something to prevent. So that's another line of research. And then lastly, any of our closed systems on the lunar surface will be additional habitats to study from the perspective of the microbiome of the built environment and the interplay between the vehicle's microbiome and the plants and crew on board or in the habitat. So these are some of the major areas that are on our mental map right now. If you're interested in more detail on most of these, you can refer to the decadal survey that we have right now. This is just a sampling of topics, all taken from the Applied Physical Sciences section, I think all of which we've actually talked about in the previous slide. And then at higher technology readiness levels, or TRLs, there's a similar set for the translation to space exploration systems. And again, I think we've talked about all of these except for closed life support. And that's a whole nother large scale topic that we won't go into right now. So there's a rich resource for thinking about this. And the decadal does a good job of this. It's not just about lunar research by itself for enabling lunar exploration or for what can you learn uniquely on the moon. We also have to keep in mind how this fits in with what we can do on Earth, on the ISS, and what we need to do going forward for activity on Mars. So to borrow a couple of Julie's slides, and I won't go over these in detail because you've already seen these, I think, twice now today. This will be the third time. So during the break, we will have a quiz. But it's very important for all these areas to think about what research do we need to do on the Earth with the platforms available? What do we need to do on ISS? What's appropriate for Gateway, lunar surface, and then Mars, both the transit to Mars and the surface. So there are a number of topics in both physical sciences and the biological sciences. Okay, so given this broad context, it's a very large palette of possible scientific investigations. What are we up to going forward as we meet today? The first point is a very important one, is we are maintaining continuity with the past. So happily, this is not 2005 and the ushering in of the Constellation program. And those that have been around for a while know what happened as a result to the OBPR science portfolio at the time. In contrast to those events, we're going to continue to execute the current portfolio of approximately 200 investigations in space biology and physical sciences. And we'll continue to use the full range of platforms that we're using now for current research and for what we're soliciting in future. Going forward, we're coordinating a lot within HEO. Those last two charts that we saw are kind of a rough sketch of roadmaps for development we need for exploration. So we're working with our counterparts, say, in life support for how space biology and physical sciences can contribute to what is needed for the next generation of technology for exploration. We're also working on providing input on the Gateway's science requirements. So the Gateway is one of these things that particularly went into overdrive with the March announcement. And so it's very early days, and happily, Brad and his colleagues are canvassing the science community within NASA, because that's all we have time for right now, for initial scarring of science requirements and getting a rough handle on those that can be refined as we go forward. So we're trying to get in on the ground floor of these plans. Similarly, with the CLIPS program, which is led by the Science Mission Directorate, we're talking with them, just as Brad said, about how we can use this contractual vehicle and or participate in missions that have room for an extra payload or two. Additionally, moving forward, we're taking advantage of a one-time budget upper we have in our budget request for this fiscal year to flesh out some concepts in a little bit more detail. Some that are most relevant for lunar exploration are a lunar biological payload, a platform agnostic biological research capability. So this is looking for a platform that we could use on Earth, on ISS, on Gateway, on the lunar surface, and thereby compare across these different environments how different biological systems are behaving. Lunar dust mitigation and deep space quantum link are another two areas. In all of these areas, we are using an approach called science definition teams, which is where we construct a team based on a free and open competition for membership. They are led by civil servants, but are populated by members from government, industry, and academics. And in the case of these early stage concept developments, their task will be to define a scope of work for the activity and a top level implementation plan, which then lays the groundwork for defining budget for the follow-on work. Then lastly, the last element of going forward is the new decadal survey. So that was a wonderful session we had this morning. Just to recap, the decadal surveys are produced by the National Academies. They provide support for new activities. I hope you were listening when Jim Green mentioned that when he was in Planetary, when he was the director of Planetary Sciences, the decadal survey was instrumental in growing the budget from 1.2 billion to 2.4 billion when he left. We look forward to the day of using the billion word in SLPSRA. It's good to have aspirational goals. But certainly decadal surveys do provide a very firm foundation for well-defined areas of growth and the attendant budgets that need to go with them. They also provide protection for highly ranked activities when the various planning winds shift direction and one needs to be able to argue for the importance of maintaining activity. And related to that is when budgets change or schedules or technology innovations come along, it's time to change the plan. Decadal surveys also provide good guidance in how to go about making those decisions. And those are often called decision rules. As you heard this morning, and I really want to emphasize this, decadal surveys are community driven. As Rob said in the session, this is one of these opportunities where we really have the opportunity to influence the course of the future. This kind of opportunity only comes up once a decade. And so it's very important. And there are things like white papers, community forums, and service on the committee that will be available. One thing that will be different, we hope, in this next decadal compared to the last one is we will have packages of work. Campaigns might be one word we use for them, and might be one form. There might be some other forms depending on the field. But this will be a body of work identified along with a cost estimate for that body of work. So that's going to require a new way of thinking. It's a challenging one, but it's very important because the current decadal survey is terrific in identifying high priority areas, but the scope of activity in those areas is not really laid out, and the budget required to pursue those activities is not really laid out. So what we have today is of the 65 areas of high priority research identified in the decadal, SLPSRA is addressing about half of them. And I think of them as 65 slices of toast, half of which we are taking our tub of butter and putting on generally a pretty thin layer. And with going with this cost estimated campaign approach in the next decadal, my vision, back to that billion-dollar notion, is we have Dagwood sandwiches proposed in the decadal survey. So for the younger generation that may not have followed the Blondie cartoon strip, that is typically a very high and massive sandwich. So get away from the thin, the toast with a thin layer of butter to a Dagwood sandwich. So that'll be an important part of the decadal survey going forward. So to conclude where we stand with SLPSRA and lunar exploration today, we have this new era of lunar exploration that's begun, and in many facets, really pretty much every facet, has gone into overdrive. This fits in very well with SLPSRA's mission because the lunar environment provides many challenges to sustainable exploration, where new ideas and new technologies are needed in order for the agency and its partners to conduct sustainable exploration. It also provides unique opportunities for scientific discovery. So we're going forward with maintaining the current portfolio of investigations and research platforms. We're coordinating with CLIPS and Gateway. We're developing some new concepts for research and commissioning the second decadal survey for life and physical sciences. And to wrap up, I want to emphasize your role as the community here at ASGSR. There are a lot of ways for you to shape the future right now. This is a very unusual opportunity. Like Chris Mason, I grew up in the Midwest, and one of my coping mechanisms sometimes is to think about an old style football game between the Bears and the Packers in the 1950s, you know, before the passing game is really developed, and it's in December and it's a combination of rain and snow and the field is mud, and it's basically 3 times up the middle and punt, 3 times up the middle and punt. Every once in a while, a big hole opens up and you've got to make as much use of as you can of that daylight. And this is such a time for this community. We have an alignment of these very aggressive lunar exploration plans, a very high degree of coordination across the mission directorates at NASA, and the kickoff to this decadal survey. So there are lots of opportunities for you to help shape our future. And I know you're very busy, you're oversubscribed, you know, your time and energy are finite and oversubscribed, but there are many opportunities to help shape the future. So things like requests for information, serving on a science definition team, participating in the workshops that Brad mentioned, providing input to the decadal survey, and even serving on the decadal survey are all important options available to you at this really important time in our future, in shaping our future. So with that, I'd like to thank you for your attention and for all your dedicated work that has brought us so far today in space biology and physical sciences and put us in very good shape for taking advantage of this new era of lunar exploration. Thank you. Any questions? Be nice if people could hear you. Yeah, there's a microphone right back there.
So you mentioned that the gateway will be only occupied for 1 month out of the year. So what is the reasoning for that as opposed to doing more long-term missions to the gateway?
I think the initial reason as it stands today, our understanding of the transportation options to deliver crew to Gateway is the Space Launch System is required, and that's our limiting factor right now, is the transportation system. A corollary to that is a thing called dollars. If we do have transportation options available, then that will also require additional funding. But the primary driver right now is I think the architecture is centered on the use of the Space Launch System, and that will provide an opportunity once a year.
Thank you.
Sandra?
These scarring conversations that Brad is going off and having with the Gateway team, are they specific to phase 1 or phase 2? Are you assuming that you're going to be scarring for phase 2 only, or are you looking for opportunities to scar in phase 1?
So
for
both.
science.
Yes, so both. So, there's an interesting cultural use of the word science in that, like in SMD, I would say there's an implicit suffix to it, science dedicated, so like a science dedicated instrument or what have you. But in phase 1 of Gateway, there is very likely to be environmental monitoring equipment that is there for safety and performance reasons. So for example, the microbiome of the built environment. There may be swabbing done as a matter of course just to characterize from a safety perspective what's happening in the vehicle. That will also be an opportunity for MOBI-based research. So in the early days, there are two things that sort of mitigate against science-dedicated work from a SLPSRA perspective. One is we don't have a history of these small instruments like SMD does, and so we're just starting that development. We won't be ready for that 24 date. The second is it is going to be a very small platform, very limited in its capability, and that will be another one. So I think we're really focused on phase 1, trying to get double use out of things that are used for safety and performance monitoring of the Gateway, and in phase 2 can start entertaining dedicated instruments.
Okay, great, thank you.
Yes, Annalisa.
So I really like the analogy of the football game and the slush and the rain and things. But in order to run through that gap, maybe we need a couple high-powered quarterbacks or some funding to get through there. Is SLPSRA also helping the PI community then to sort of embrace this opportunity? Is there going to be, you think, more funding in the near future that allow us to storm this gap and take advantage of the climate?
We are going to be working very hard on that, Annalisa. It's kind of a chicken and egg thing for sure. Well, so maybe the chicken and egg breaks down because the way the system works, we're not going to get a check for a certain amount of money for activities to be determined. We did get a little bit of seed money to do some early concept things, which I described. We need to take those ideas and others and flush them out in order to make a more concrete request, for specific amounts of money. So I cannot promise any particular success rate, but it is definitely a prerequisite that we have well flushed out concepts. And it's not necessarily for the community to come up with the budget estimates. That's maybe more in our bailiwick until the decadal comes out. But that's a necessary step for budget growth, is to have well-developed concepts in mind. And we'll be pushing that hard. Okay. Right. Thank you.
So again, thank you, Craig. So thank you all for staying for this symposium, and I want to very much thank our 3 speakers. And for that, I will turn it back over to Kevin.